All right, hello everybody, and welcome to an exam one review session. And sorry for the cramped, pre-planning would have been a good thing. Bulldog race, no, it's Bulldog race's fault. We don't just all blame all of them. Diana helped us get this all together. All right, so here are the various problems that I have uploaded. We could either do some of these, or we could pick rando problems. I have on the laptop here, I have like all of my University of Hartford things, so I can probably find some old problems maybe without giving away the old problems I intend on using. What would you like? Anybody gonna call something out a type of problem or anything?
Can we do this one?
Sure. It's too long for an exam.
Sure. Or
Just
like
go make that clear.
H or just do K.
Did you say any of the problems had material that wasn't?
I didn't hear the middle part.
Did you say if there was any problems that you posted that had material that wasn't going to be on?
I don't think so. I don't think I said anything along those lines. I was asked by someone earlier today if we were going to do like a statistics thing, and I said no, because that's not as important to me as the other thing. That was in a P set where we did some statistics. And I'm like, that's, I just wanted to introduction and to make the connection between.
Did you post anywhere online which chapters will be on the assessment?
In the exam module, there is a brief thing that's describing what the P sets were, and that is in essence what is fair game on the exam.
Okay.
Right. So, but if you wanted to put it down there, there's quite a bit of chapter 3, an itty bit amount of chapter 4, a fair chunk of chapter 5, and a fair chunk of chapter 6. So it's 3, 4, 5, and 6. Chapter 7 is on exam 2, as well as I think chapter 8. I think chapter 13 and chapter 14 are all going to be on exam 2.
Thank you.
You're welcome. All right, so for this, we should probably get the cross-sectional properties. I would definitely give you that, just because that's just a waste of time, and there's no there's no point in trying to ask something that I'm sure that you could do if you just had the time for the thing. So for most problems like this, we would get the geometry. I would give it to you. So oh no, the pen's running out, and I have replacements for these, but we're gonna have to change to another. I don't need to write. Oh boy, Lord, it's terrible. Oh, that's awful. I'm having traumatic. Oh, that's bad. Oh, that I no. Not gonna do that. That's disgusting. Okay, so I guess we'll go in dual mode. So it's back to this thing again. Sorry about that. Let's go back up. I'm gonna go right screen 2, and also HDMI. And as was pointed out, I think the upper one should be this one, right?
Maybe it doesn't do anything.
That's not what we want. You hate me and I hate you. Everybody hates each other.
I'm so sorry.
It's not your fault. It's just my life. I took your sweater off. That's what happened. Said the sweater was cool, and then I don't like cool this one. Gotta be smart. I'm so sorry to have to do this. I don't know. When you're unsure, turn it off, turn it back on. That's all I teach people.
Office hours and the markers you should not raise.
I mean, that liquid is a lot better.
Oh, really?
Yeah, that's usually the one we work on.
I think we're gonna have to stick with this. My bad. Oh, it didn't come down. It just hates me. All right. So, yeah, as mentioned, it's about too long. So,
It's okay, you don't have to do each.
yeah, we don't have to do both. Let's just get let's get as much as we can out of it without having to go into crazy pedantic. All right. So anyway, we can take a look at the connection right, the collection right here, and we know that we'd have to do FBDs of all the different three directions, simply because by observation it'd be easy to miss one, right? So, and this problem is a little messed up because the author decided to come from this direction. So, I think, I think we're going to be okay. Yeah, I'll leave it the way the author did. So I'll start out with the YZ direction there, and just draw it in here. Not going to be my best effort here, my best work, I should say. But you got your 2,000 pounds, and you got your 1,500. So that right there is really the important thing when you're doing one of these problems, is to look for these competing type of problems, these competing reactions. And I'll just put it in there. Whoops, going back. And you don't know which way it's going to go. Is it going to go clockwise? Is it going to go counterclockwise? It depends on the values of these and these combined with each other. So when you have that moment about the x-axis right here, and that's what I would probably, if I was testing this is what I would test on. That would be the essence of the problem, is that like you need, there's a temptation to just jump through and look for and gut feel it, because there's lots of problems where we did that. So this is what I would say is the nature of this problem, where you would say counterclockwise and your 2,000 times your 18, and then measuring whether you picked which, if you picked the correct number there, and then minus the 1,500, and then times 9, and then I would usually pick that as a counterclockwise default, and I might stick an R there just to make it clear that we're talking about a reaction. I don't always do that. And we don't have to do it for every one of these, but I believe this is going to be about the x-axis, right? So it's going to be about that axis that we're going to put in. I said about the x-axis we get 22,500 inch-pounds. And as a reaction, let's see, on my stump, I was counterclockwise, so this must be clockwise. So it turns out that that makes sense. The 2,000 times the 18 was larger than the 1,500 times the 9, so the reaction had to go and go clockwise. But on the stump, what will end up happening? That was not a good stump. Let me try my stump again. On the stump, when this thing's left over, like here in the, this is, in this case, the author decided that's the X direction. That instead of the reaction is this guy right here. That's the reaction. The resultant was going to be in, let's just put X, MX, right here, going in the counterclockwise direction. And if our main part of this problem was to look for H, this would be the moment we would want to get, because it would cause tension right there at H.
So H is on or off the stump?
H is, well, we've cut the thing right there where H is. So you can almost think of like half of H was on the free body diagram and half of H was on the stump.
Can you repeat why we don't use the reaction moment and we just use the applied moment?
All right, so you can do either one, but for my personal preference, I think the stump is easier to communicate, and also for me to just a little bit easier for me to see. You could look at either one of them and kind of get the essence of whether it's a tension or a compression. That's usually what I'm looking for. But in this case, the stump, usually you get the sense like, oh, I can look at that moment and I can kind of see that it's going to pull on that element. Over here on on this guy right here, let me what do I haven't used? Let's go out there. So the actual reaction is that direction, right? So if you're looking at H right there, you could see that that's going to be in tension from there. I don't know. It's when I was first introduced to the book for which this problem came and lots of other things, for me, it like very much cemented. Like I kind of knew all of the things, but when going through and using this textbook, I was like, oh, I like that better. I make that distinction between the reaction and the resultant onto the thing and get that sense better.
So just to confirm, we see that the pipe is bending down. So using our intuition, H is in tension, which is a force going away from the pipe.
Yes, in on the free body diagram, it's going away from me. Yeah.
Thank
you. We could keep going through this problem some more to see the combined nature of the thing, if you'd like. Okay. We'll keep going with H. Is that all right? We don't have to go to K. All right. So you also see on this that just from observation, but also from right here, that right there is in line with the axis of the main tube, right? So that's going to cause a compression on H. You can see that it's pushing towards H. You can also see the reactions also pushing towards H right here, right? The reaction is also pushing onto that element. Either way that you want, like the first way that I mentioned is sort of like the perspective of the resultant kind of thing, right? That force, all the forces that are on the end of this thing get pulled down onto this piece right here, right? And then also all of the moments that are a resultant of moving those forces over from where they're actually located to the place we want to know, those also get placed onto the stump. Let me go with some numbers here. So the bending was going to be that MC over I, and just as a, to make sure we have bending of H was the 22,500, and then the I, this thing was apparently had an outside diameter of 3.5, so that's, I'll just put 3.5 over 2. And then the I was something that you would be given, and it was 3.017. And that was, I'm going to put them in KSI, so just divide by 1,000 as I'm writing the thing down. KSI, and that was in tension. But then we also have the axial in here, and this is the F over A. And that F is going to be from the 1,500. And the area, which we hadn't put it was a 2.228 right here. So okay, so this is a much lower number. Usually axial is pretty low, so it's 0.6731 KSI, but compression. So it's only going to change very little bit on the overall normal. And then we also would have found torsion in here, and let's go for this guy right here. And just looking down the axis, you would see, let's say, I don't have a good spot for it, so I'll put it right there. So here is the FBD in this direction. The only force that's going to cause torsion is going to be this 3,000 pounds. So it's going to be 3,000 pounds times the 9 inches again. Right, so the MZ in this case is the same thing as torque. And we could just, from observation, say 3,000 times 9 is 27,000. Did I get that right?
Yeah.
Wow. Little things. I can just impress myself with that thing.
Yeah, I had a question about the moment of area, because I don't know what meter diameter you use. So you use like 3.068.
For this one?
Yeah, for this one. And then it says 3. And I just don't know.
Yeah, I probably was just being a little clever. And that's always dangerous, so I apologize for being clever. I'll try not to again. But it's just that a 3-inch pipe actually doesn't have a 3-inch inside diameter. It's just weirdness of the nominal world.
For the geometries of pipes, you are supposed to.
I would just give it to you. Yeah, I'm not. That's not something I'm going to measure or time. So I'm sorry about that. Yeah, I was just joking around about it. I'll try to be clever all the time. It's my obsession. So 27,000. I would just give you the cross section properties.
Like the area.
I'll take him the area. I give you the A, the I, and the J.
Like,
I'll just give it to you because I don't want you. It's not. Just take time.
Yeah. Sounds good, thank you.
So anyway, so we got. So we should go on to the shear stresses. So we need the TR over J right there for the torque, and in this case. We notice, and you know, these are little ones that I know that people get, this is an important type of thing. So I'll kind of write it on top of here just because that might seem right. So the torque is kind of going this way. So if you, I did not pick a I don't like the orientation of my, my guy over here, so I'm changing it. So I guess Z down looks a little bit better to me. And so if we're on this face right here, that would be the direction that I would say that the shear is going across H, like onto the positive direction like of Z across that face right there. We don't know about the transverse shear yet, but that's the one that I would put on there. So let's put a pin in that. So that's the 27,000. It's the same 3.5 over 2 and a J that's going to miraculously appear here in front of me of 6.034, which, okay, 7.83 KSI. And then lastly, we have our transverse shear. Now, I kind of tend to, I mean, I'm giving away things, but I tend to not ask this. I probably wouldn't ask this on this exam because there's so many other things to already look for. And kind of in the beginning of the semester, we're just trying to get visualization and try to see those combined stresses and those types of things so that we can make some comparisons to FEA. But mostly what we care about is things breaking now. So we probably want to go for the worst case for something and then neglect the transverse because it's just kind of a detail that sort of gets in the way. So I'm just doing this here just for, I don't know, completeness. So we won't spend too much time in there. So that's going to be, okay. And so like you look this up for a hollow thing, and I think it's 2 times V over A for a hollow thing. And then you have to ask the really most important question here is which forces cause a load, a transverse stress at a H? And the answer is 3,000 pounds would be the one. It's going across that way. And so H is to the side of the force. And that's kind of like the best way I can simply describe why you would, when selecting which force is going to be the one that's going to cause the maximum. That's how I would say it. And you notice that it's in the same direction as the shear was, the torsional shear. So those shears are going to combine together. So that's the essence of this problem, really. is getting the correct moment when you're faced with a choice of something like that. Once again, that's more near the beginning of the semester than what we've been doing here, but still could possibly be a thing that I would ask at some point. But and then also getting the whether something is tension or compression, and whether when you have multiple ones that agree with each other, and Murphy's Law is trying to get back at me again. And then also whether the shears agree or not. Do I need to go any further on this one?
Can you re-explain why those two forces are on the bottom of your stress element, and then why they point in those directions?
Okay.
I understand the torque, just less the transverse shear.
Okay, so the transverse shear it's because of this 3,000 pounds, right? That one, once again, it's always so much easier sometimes with the stump to see. This is the 3,000 that's coming there and going across the section. If we were to look at it, it would be that section right there, and here would be our little guy H. And if we look up even from the diagram in the book, I wish they would put an arrow in there that they could show you that they're showing the stress distribution as like just over to the side of it is like a parabola, right? Where the maximum ends up being there at the side of the piece, right? So that's the reason why I'm putting it. Where did you go? Go back to me. That's the reason why I was putting that purple one down there across, because it's going that way across the face.
But why on the bottom and not on the top of your stress element?
Oh, because of my axes. I chose an X right here and a Z right there. So this is like the bottom of the stress element is going towards the Z axis that way. So I have it oriented that way. The way I've drawn that axis really poorly, kind of in the way. I liked that one a little bit better than what I had previous drawn, which was like kind of rotated.
And I'm a little confused why it couldn't be pointing left on the top of the stress element.
I just kind of like went like this right here.
Yeah.
that right now, this moment, that seemed more appropriate to me, was to go flump like that.
Yeah.
Okay.
How
Yeah,
much
okay. Thank
would draw like the other lines, the other like shear lines pointing towards that?
Oh, I'm sorry. Like that?
Yeah, like eventually when you're.
Yes, when I got done. Yes, yeah.
Okay, sounds good.
So we just look at like, since the force is applied this way and it's on that side, like we just follow that direction, right?
I think what you said was right.
Okay. Like
There's a lot of that.
since the 3,000 is applied in the x direction that way, and it's that means you're saying that that's applied to the bottom part of the stress element, right? Like
Yeah.
it's a geometrical thing, right?
So So what I've drawn right here, I was thinking this right there as I was drawing it. Like I was thinking of like that whole thing. We threw it away, and we're just looking at the stump, and it's going across the face
Right.
of the thing.
And the same with like the moments, whichever direction, like torsion, for example.
Yes, with
like,
the
it's
torsion,
applied
yep.
that way, it goes that. Okay.
Yeah. So because the torsion was coming that way across the thing, so you kind of see that's kind of going across the face
Okay.
of the piece right there, especially when it's a shear going across the face.
What happened to the normal stresses?
Oh, I just didn't draw them on there.
Oh.
I'm sorry. Yeah. I was trying to be fast, but I did a terrible job of it. So that would be so it would be the 13.05 minus 0.63. So I think that came to 12.4 is what ended up going there in the Z direction. And this ended up being, because they added up together, I didn't ever wrote this one out, but this came out to be like 2.69, I think that's correct. Yeah, to PSI. That was a little tiny bit, little PSI. So when they combined together, it was still going to be like, oh, is that true? I'm looking at the numbers here. 10.5. Oh, that's 1,000 right there. Okay, yeah, that makes sense. Okay, so with the total, and then this would be call that XZ, where we had the that turns out to be 10.5 KSI. All right, so another problem.
I actually have a question about the previous pressure vessel problem.
Okay.
In the solution, you use the equation for the average tangential shear stress, but then there's also an equation for the maximum tangential shear stress. So I just wanted to be clear on like what case would I use the average versus the maximum shear stress in the tangential direction.
Let me just be really careful here and see so I answer the right way. I think I said determine the absolute maximum shear stress on the outer surface.
Right.
When you have the outer surface, the only equation that we have for thin wall is called the average. I don't know why Shigley does that, but that's just the case. He's got two choices. One is going to be the maximum, which turns out to be, that's the inside surface, and the other says average, which just you use because that's the only thing we have, right, for the outer surface.
Okay.
I would just point out that I think Shigley is being there's not many other books that bother with that because the thin-walled is often called the thin-walled approximation. Right. So I don't know why he's being so very specific about an approximation.
Because the idea would be that it's thin-walled, so it's the same on both.
Yeah. So you're not really worried about
so
too much of the
use the average.
But if you wanted it to be really accurate, if you ended up using the thick wall just to check, because even though we call them the thick wall, I believe they're always true. They're not an approximation. They're a geometric result. He's leaving, and I didn't want him. Oh man, I'm sorry. I feel bad about the room being oversized. Yeah,
Can we talk about the first stress concentration problem? Because I don't know when we should use brittle Coulomb more and like modify more.
Okay.
Seems like brittle Coulomb because it's the most conservative.
Is that the one that says just the one that says Collins? The one that's out of Collins?
I think so.
That looks kind of like oh look, I have it right here too. I could have just looked right here. This guy?
Yeah.
All right. Sure. So we have a mounting arm. It's made out of class 60 grade cast iron. The arm is loaded by a static axial force of 225 kilonewtons and a static torque of 2,048 newton meters. That's very specific. Can this arm support this load without failure? So, first thing I might do, if I hadn't already been given, would be to look up what the tensile strength and the compression strength would be. So 62.5 KSI, and of course this is given to us in metric, so I would do the conversion. I would not make you do that. I might have thought about it at one time, but I think I've given up trying to do these kinds of time-taking things in favor of other more important things to measure. So the first thing I do is go to the figure. Let's see if I have. Well, you can just take my word for it, I guess. Or I guess looking at the figure, we need to find big D, which is going to be this guy right here, over little d. So big D over little d is going to be what, 56 over 50? Based on these. Which is going to come out to 1.12. And then an R over D of, let's see, that's 3 millimeters. And then make sure we're using the correct D here. That should be 50 over the small one. So 0.06. And if you look that up in tape figure A15-7, make sure we're using, let's see, okay, so we have both, we have both axial and torsion. So I want to make sure that I'm looking them up in the right one. And I'm not sure which is which 100%. So going back from context, it looks to me like we have KT, and then I'll give it a subscript. We'll call it axial, is approximately 1.9. And then to apply that, we need to have an area which uses the small diameter there, right? So pi over 4 and then 0.05 for the 50 millimeters. And 1.963 E minus 3. And so maybe you would have to find that only because there's a chance people would use the wrong area for something, the wrong property for something, or they would not look into the caption of the stress concentration and see like, oh, that's the area property or the cross-sectional property that goes along with this. There's not many in this book that have that big distinction, but there are a couple. So anyway, so we're going to have what the maximum stress. This is not von Mises. This is just the normal stress. Is just going to be that KT. We're not applying anything. There's not a fatigue problem. We're just using the stress concentration just straight in because it's a brittle material. And so that's going to be the times the F over A. So I can do this in one step. 1.9 times our, I'll put it all with 22,000. That over my 1.963 E minus 3. And then in my head, I'm going to divide by 1,000,000. So forgive me for not writing it. 217.7 megapascals is our value there. I know this is not symmetric over here, but I'm going to come back over to the left-hand side and go for the KT. It's actually KTS. So the torque one is approximately 1.4. The J to use, all right, the little blue's going. Pi over 32. We should have like a soundtrack during class. Should have like a. What's that? It doesn't actually have music. Like, it doesn't fit. I'm getting it about 0, 5, 4. All right. It's 6.136 E minus 7 and fourth. And then we could find what the maximum torsional stress is going to be. Our KTS times our TR over J. I guess I'll write TR over J. And so we have our 1.4 times our torque, which was 2048. And we take our 0.05 divided by 2 here in our 6.136 E minus 7. And I think I got the right number here. All right, so always smart to summarize and say, okay, so there's no particular spot that it needs to be on, no plane that it has to be on this because it's axial and torsional.
Like when you're looking at the graph and it's like the D over D doesn't map directly to the line, are you like doing the space in between the two lines, or are you like roughly estimating above or below to like the closest?
That's worth. Thank you. This is a great question. That's worth taking a look at. Let's see. What have I done? Here, because I mean, it's not a trivial thing to find numbers on a graph. I've known people to get it wrong a lot of times. I got it wrong. I said known people. Those people being me. It's pretty easy to get it wrong. So let's see. The first one we had here. Let's see if I can. Is my pen gonna write now? Do it again. It's like blinky here. Is this pen right? Okay. Let's see. So we had let's look at the torsion one first. We had a D over D of 1.12. Well, that's pretty, okay, so we're dealing here with a 1.09 and a 1.20. I would say it's going to be really closer. It's going to be closer to the 1.09, right? So you kind of like do a mental interpolation going on right there. 1.09 is almost 1.1. So 1.1 to 1.2, going to bias pretty close to there. So if I were to draw a line, I'm guessing it's going to be something like, but that's actually probably, well, it's making me erase like this, you son of a. That's not the words I have in my head, but it does seem like to be a triangle. So I'd actually probably have gone like maybe even a little closer. All right, so that was worth it, right? So what do we have for the others? 0.06. So like right in there. So something like in here. I said 1.4. I could probably argue with myself in the past. And I might even say that my 1.6 is actually more like right over here. Because this is, excuse me, I said 1.6. I said 0.06. Right here is 0.075. So probably right in there. I only take off points when there's like 0.1 off. So you obviously, if you were to pick 1.5, you did something really mixed up, right? It's a little dang, but it's not a lot of dang. But if you had like 0.2 off, like you really did something wrong. You're probably using the wrong graph, right? Same thing for coming up to this guy right here. One of the reasons, okay, so here's a much bigger jump between, so this is really going to hug the 1.1. So probably somewhere like there. I probably want, what I said, 1.9, because this right here should be 2, right? And because that's 2.2, so this should be 2 right there. So once again, I don't know. I might argue with myself in the past and go 1.8, but I wouldn't. But I'd look at the thing and said, you pick 1.8, I pick 1.9. You know, I'm not gonna hold that against you. Generally speaking, I try not to hold anything against you. Okay. So we got these. A good thing to do is to label a stress element, and this always drives me a little nuts. It's like, is it going that way? Yeah, it's got to be going that way, right? Yeah, okay. So it'll be down the face. So I can almost convince myself that it's going to go up the face. Yeah. I don't like that. What happened here? I'm gonna blow this. I know. I think it's going down the face. You agree? Yeah. With the way that thing's drawn? I think it's gonna, yeah.
Where in the figure is your stress element?
Good question. Somewhere in here.
But like facing which way?
I know, I got you. If that is the X direction, it's going that way. I'm not committing to what the other one is. It doesn't matter. I mean, if I want to, I can make it go like Y, if it just makes us feel better. And then we can say it's right here, if we want to.
Thank you.
You're welcome. So we draw all this onto here, and we label this 117 MPa, and this 218 MPa. If we were giving an answer, but now our important thing to do is to find sigma A and sigma B. So we have to do a little bit of our good friend Moore circle. We don't have to. We can probably just use your equations. Sometimes I will ask for a Moore circle, a drawn Moore circle, in which case you got to do Moore circle because I want you to draw. But otherwise, if you just need the principal stresses, just find the principal stresses any way that you want to. If that includes Moore circle, that's great. And I know that people would like me to plot these correctly, so I will attempt to. So I'm going to plot this face first. So probably actually easier to plot this face first. That face first is going to be counterclockwise, so up and approximately half, not quite, of this other point right there, right? So this guy right there is maybe 0,117. We could use the real numbers, but I'm just really quick. And this spot right there is going to be 218 and call it negative 117. So right here is approximately the center. It's going to be 217, 17.7. I really screwed that up. Plus 0, but then let's divide by 2. Or 108 point. Woo! Shoot. Wow. Something I do with my palm just not today. Thank you. 108.9. And then the R, which is right here on this, is, we just use C, 108. These are always the easier ones to do. And then the 116.8 squared. So we get an R of 159.7 megapascals. So then it's also going to be the absolute maximum. And if we draw this, oh, I had such high hopes. Nope, it's just getting worse. We're gonna let it die. Okay, let it die ugly death. And while we're there, we could also put in that guy and that guy. Should have colored them better. But anyway, that's going to be the sigma A and the let's go purple. Sigma A, sigma B. The two non-zero principal stresses. Sigma A is C plus R, or 108.9 plus 159.7, and so 268. Squeeze them in there. 268.6 megapascals, and then sigma B, C minus R, 108.9 minus 159.7, or and by the way, we call that a tension. And then this one we don't have to put a negative sign, just put that as compression. 50.80 megapascals compression. And now we wanna find, I think this is asked for brittle Coulomb more. You could have asked for modified more. I think when I wrote this, I was doing this, I stopped doing modified more, because it was just kind of, it's not no pun intended, more conservative to use brittle Coulomb more than to use modified more.
How do we know what's asking for that?
There's no way to know from I didn't think about it when I put this together. I just I hadn't, but I hadn't in years. I hadn't done the modified more until I came here again. And I was like, you know what? It's not. It doesn't take that much more to do the modified more. I keep saying more. It's very distracting to me.
So should we just do this?
I'll ask specifically for it. You'll know what I want. I wouldn't ask it this way.
If it's unspecified like this, and we get to the point where we have our tau xy and our tau or our sigma x, can we just use von Mises and then just say if it's less than is that also acceptable?
I think in this case, we're trying to establish that it's a brittle material.
Okay.
And generally speaking, you would use the brittle Coulomb more
Gotcha.
or the modified more for the brittle material. And I'd also mentioned to other people that if you just said on the paper, I declare that I have used this technique right here, that's probably acceptable the way that I phrased this, right? Because honestly, like I don't want to be creating or help fostering the mentality of I will do what you tell me to do. I want thinking people who think. And so if you express, when I ask when is thinking a break, oh, that's a great question to an engineer, and then you answer. But you answer and you make it clear that you know what you're doing and you understood what that's like, yay, 100. I like that. Cool. Once again, I'm not looking to take off points. It's not my goals. So the last thing as part of this, but I don't have enough page space. So we're going to steal here. I'll say keep. I'll delete them later. I'll delete them later. Come back up. So we want to take our brittle Coulomb more, or any of these. I think are best explained by when they have these mixed things, is to go apples to apples. So that's a 1 over sigma A. That's a capital. It's sigma A. SUT, right? Those are both tensile types of stresses and strengths, minus, and they're just being very pedantic by putting that minus in there. But they're not the only people, by the way, so it's not Shigley's fault. Everybody puts the minus in there. But just recognize that it's not really minus, it's just recognition that it's a compression. So we're gonna end up doing a minus minus. So we said 268.6 was our tension of principal stress. 430.6 was our ultimate tensile strength, and then we had minus 50.80 and 1,292. So you can see that this ratio really is not going to play much of a part into the answer. Because that's 50 divided by what, that's not a whole lot. So your brittle Coulomb more safety factor is almost entirely because of the tension, and it ends up being 1.51 is the safety factor. And if you were to have to plot it, the plot goes like big little guy, big guy, little square, big square, boom, boom. And this is not going to be a very, because that's sigma A, sigma B. It's going to be like really, really tight in there. And you can guess that 1.51, it's not going to be too close. It's not going to be the halfway point between there. Something like that is where the line would go. But you would see that if this was a modified more, it gets kind of boring, because the modified more keeps extending the same amount downwards to there as this is tall, and then makes this thing over here. So the modified more would be just be comparing off of the, it would not be using that 1-to-1 ratio type of thing, which is kind of the important line distinction for a modified more. Did that help, Bronx?
Yeah. I was wondering if you could go over a 3D Morse circle example.
Okay.
And the one on the view sheet only has like 2 axis stress. Would we ever see triaxial 3D Morse circle?
I don't think I'd ever do that.
Okay.
No. It's, yeah. It doesn't happen a whole lot. Kind of tough to find a scenario, at least on the surface of stuff. Yeah. Inside surface or outside surface. If you're like an internal thing, you'd probably some amount. You could find some orientation where they had to go in.
Are all the types of graphs we've gone over that could be present in the exam present in the textbook chapters? Or were any from you?
But where did I invent any? No.
Or they're all mentioned in?
They're all in the textbook. Yeah, yeah. And you know the main players are definitely the 3D Morse circle or any Morse circle. Trying to think. Sometimes the shear yield or the failure and what did we say? Loci, I don't like it. I don't like it at all. I want to go like loci. The portal of locus. So that failure drawing like this one, or the maximum shear stress theory, or the von Mises distortion energy theory. The fatigue ones, the SN diagram, and the alternating mid-range. Those are really the big diagrams that matter to me. And the Shigley and other people taking this course around the world. So let's see if we can find a Morse circle that's not terrible. This is problem 1. Let's see if that's the one. Okay. Oh, I see what I did. I said this is too short of a problem. I don't know. I don't know what I was thinking when I said that, because I could ask a problem that's short. So I don't know. I don't want to argue with me, but I'm not afraid to argue with me. I think I'd win. So anyway, we start out with the Morse circle here, and what do we have? We have a compression intent. Yeah, this one's not as exciting. Well, I don't think any of them are exciting, but we are plotting a face right here. I'll plot that face first, and that's going clockwise with a positive. So 14 and 10. I'll approximate like right something like that. And if we wanted to go 14 and -10, we wanted to mark that spot, and then we're going to go compression. So here's the other side of the 10. Okay. And then here's maybe this is where 8 is going to be. And so that's going to be -8 and a 10. Now, so quest to try to draw a circle through this. Well, first things first, we do go right there, go on our C. Looking at this, if this guy is going crazy. It's probably my fault. I'm doing something wrong. R right in there. Okay. Now I can attempt. Well, that's just sad. Okay. But anyway, C is going to be 14 plus -8 divided by 2. I don't have it in front of me, but let me see. Is that going to be 3? So be so pleased with yourself. R is going to be, let's see, we'll go this length right here. So it's going to be 14 minus 3. So I'll write it out. 14 minus 3 squared, and then we'll have 10 squared. So I'm gonna say that this must be 14.9 because that's what it says on my sheet right there. I don't have any different things. So I saw that with an 11 squared. I could actually almost see it from here. 11 squared. Yeah. 14.87. These are KSI. This is also equal to tau abs max. I can see that right away because I can also picture that this has to, if that these have to be the principal stresses right here. Sigma 1, sigma 2, and sigma 3. So another more circle of this, and another more circle of that, and label this tau abs max. I think I think I would consider this a fully labeled Moore circle. So if I say something fully labeled Moore circle, I mean like this. But once again, I'm not trying to rip people off their points, but you know, the important things are the principal stresses and the absolute maximum stresses. So sigma 1, which is also sometimes called sigma A, C plus R. So we're gonna have 3 plus 14.87. Even I can do that. 17.87 KSI is going to be first principal stress. Third principal stress is going to be C minus R, or 3 minus 14.87, or a negative 11.87 KSI. Is that okay?
Is there any difference in using principal stressors or labeling them as like sigma A and B versus sigma 1, 2, and 3?
Only that the sigma A and the B is just being particular in saying we're only going to use the two non-zero principal stresses. It usually just assumes something is on the surface, so it doesn't have. So it assumes one of the principal stresses is going to be 0. So instead of saying so they're just trying to be generic and be clear when they're using the loci. See, I did it right that time. The failure loci, the sigma A and the sigma B there. But there's no other reason for that. So a lot of people looking at this one.
Can we look at the first essay diagram problem too? Because I didn't understand like how you got the top line. You did one line, like the first horizontal line.
That guy? Let me see. 2-inch diameter bar ground from a field, 1030 steel, loaded in completely reversed torsion. Determine the fully corrected endurance strength SE, the estimated low cycle fatigue strength at 1,000 cycles. Sketch an estimated SN curve for this material based on the above, and the number of cycles to failure if the reverse stress is 40 KSI. So let's see if I can figure. I wish I had numbered these so I could figure it out without having to flip through. You and your thinking. Okay. So first off, this is definitely going to be in the 9th or 10th edition. The fully corrected endurance strength is probably going to have a surface, a surface factor that's based on the ground. That's I'm guessing based on my phrasing and emphasis of the ground aspect of it. If you're using is the 10th edition here. So we get to this part right there, and we see the A and the B. Yeah. The ground, I guess, 1.34 for A and negative 0.085 for B. Okay, so I'm using the ground, oops, the ground, just cross it out. So, if we want to, come on, get out of my way. There we go. So KA here is going to be 1.34 times the ultimate raised to the negative 0.085. And if you do that with a, you got to look up the properties, right? So for a needle 1030 steel, that's in a lot of times once again, I'm not going to ask where to find these, but that is something that we don't do a lot, so it gets a little bit buried in there, that skill set, that particular thing. A needle is like, I think it's like A21 or something like that. It's like A20 is usually where we end up going, but a needle is like right here in A21. So what I was asking for was a 1030 annealed. Did I say that? That doesn't look like the right properties. So I had 46 and 62. Oh, there you go. Yeah, 46 and 62. There you go. 46 and 62 KSI for the yield strength and the tensile strength. So the ultimate strength is 62. 1.34, 62, and 0.85, and that comes out to 0.9435. This thing is completely reverse torsion, but it's a diameter bar, so you have to use for KB. I think you should be using it because it doesn't say whether it's rotating or not. So that's something I should probably have mentioned, whether it was rotating, because it doesn't appear that I used a oh, come on back. It doesn't look like I used the equivalent diameter. So I guess I have to assume that it was rotating. And if you have a problem like that where I'm not clear, you could always bring up the exam and ask me. I might have made a mistake. Or you could just write that you assume something. So you assume something, okay? Because I didn't tell you. What am I going to do? Assume rotating, sorry. So if it's rotating, then you do use the diameter. And so KB is, I don't have the equation written out here in front of me. Oh, I discarded it. That was stupid. KB, I probably wrote out in here, and it's 2 inches. So that says less than or equal to 2 inches. So that's the equation to use for this. The point 879 107. Okay. So sorry for erasing this, but that was this was 0.9435 AB. I don't remember what the equation was right there. I didn't have it in front of me. I should grab the book right there. That's the difference. 0.8167617. KC, this is because this one's torsion, we go 0.59, and then they don't say anything else about temperature or reliability, so those are simply gonna be, equal to 1. And KF we never use. SE prime is equal to 0.5 times ultimate, which we established earlier was 62. So 0.5 times 62. And so where'd you put it there? 31. Okay. And so SE is going to be 0.9435, 0.81617, 0.59, and then 1, and then 31, and then we're going to equal to, I have 14.1, but usually I did have another decimal place in there, and that's KSI. The next part of it, I would look up and find, well, okay, so first off, I need an F. And if you go to that chart, which I think it's got different numbers, I think it'll be different additions, but you'll see that it ends at 70 KSI ultimate strength. But if you look at the note below, it says if it's below 70 KSI, and I think also below something like 200, something megapascals, just to use 0.9. So you use 0.9 for this, and then so you, I think it's a useful thing to usually calculate that F times ultimate. So is that 62? Wait a minute. You think it makes it look just ever so slightly quicker, and you're going to have to graph it anyway. So that's at 55.8 KSI. And so when doing the graph thing right here, I didn't include the intermediate numbers. For whatever reason, Excel won't do that. Anytime you see me, I actually literally just take little number splitters and put them on top of the thing. But this is 20, 30, 40, 50, 60, 70, 80, 90. And so we're 62 right there. And then at 1,000, we're 55.8. So somewhere kind of right in there, I think. And then here at 1 million, we should be at 14, which is, I'm guessing it's somewhere down in here. So that one disappeared somewhere. Where'd that guy go? Something like that. We also need to find out what A and B is equal to. A is going to be F times SUT squared over SE. And B is 1/3 log base 10 F SUT over SE. And here is kind of where we get some benefit out of Christmas colors. Having done this 55.8 squared over your 14.1, hopefully capturing a little bit more sig figs there. 221.067. That's too many sig figs. And then here, negative 1/3 log base 10, 55.8 over 14.1. So negative 1993. Not a bad year. And then to finish off here, if someone gave us the 40 KSI right here, come down and expect it to be somewhere close there, but it's really easy to get this wrong. Really easy to get the log. The pencil width makes a big old difference.
How do you know the negative slope for the first 1,000 cycles? And then why does the third part of the line start at 1,000,000 cycles?
Well, the answer is probably just because they observed that over time. They observed, when they did the tests with steel, it had these traits. So the last part for the million is the need, and I can't exaggerate probably too much just how crazy scattered the nature of this thing is.
Okay, so it's always SC
Yeah.
at 1,000,000 plus.
Yeah.
And then you can just draw an arbitrarily somewhat shallow negative slope.
I don't know if someone arbitrarily, but see over here, life is a lot more complicated than that line.
Right.
So we don't really do anything with low cycle fatigue, but
Okay.
it kind of goes. It's that this line. We're very confident with that number right here.
Yeah.
Probably a little less confident with this guy right there. Experimentation came out with that one graph that for F that kind of lands that right there. It sort of gives us sort of this quasi slope, if you will.
What is the rightmost point that you put in purple?
This guy right here.
Yeah.
That's all. Well, okay. So that is F times SUT.
Okay.
And that's where we have a graph of F versus, once again, a little weirdly, versus right here, but it kind of dips down like that right there, and we get 0.9 as the lower limit of the thing.
Thank you.
You will. But can't exaggerate how much of a scatter we're drawing. We're humans. We like to draw lines through dots.
Can I see the table that you got your KA from, your service fashion?
I hope so. I don't know. I'm gonna keep it this afternoon. Throwaway society. Oh, I didn't. You guys were on break. I didn't get to brag about my changing out of vanity. I changed out the vanity in my bath, in the master bath, after months and months. And so I was talking about throwaway. I was talking about throwaway society to have a vanity to throw away. I know it's exciting stuff. So here is is this the KA?
Yeah, but you used 1.21.
Did I?
Yes. And something else.
For this problem?
Wait, sorry, what?
I
What
said
edition?
use 1.34.
What edition do you have?
This is the 10th edition.
Yeah.
Yeah, I don't know why it's so wrong. But then also talk about some crazy scatter there. One of Shigley's other books has shows like more of these where these coefficients came from, and it even has a big note underneath it saying this is terrible. The scatter's not crazy, but we drew a line through it anyway. Used to have this guy that I worked with that collect data for gas turbine emissions stuff. That was like a side thing that they were doing, and they like advertised what their doohickey did, and he would bring me like videos. Can you make the graph go like more like this? I'm like, the graph's gonna do what the graph does. I would rather you draw it like this. Sorry, can't make the curve do what it didn't do. They could back in the old days. The draftsman just use a French curve through things. I'll make that data do anything I want it. I'm like a dance. We can talk more about this stuff instead of that.
I was just wondering, why you had to assume it was rotating for KB.
Good question. Is when you're coming down to this piece right in this area somewhere in here. For some reason, this is angles for someone not as tall as I am. I'm trying to see where would it say. Okay, so in here we could get the inference from it Area of common non-rotating structural shapes.
We don't use that.
So
We just
we
assume
would-
it's rotating.
Yeah, so we would assume that one was rotating. But if it's round, even we would have an equivalent diameter for something being round, which already has a diameter, but now it's less. It's a less of a diameter if it's not rotating. It's all about the apples to apples. What they're trying to make these like okay, if your thing isn't similar to the test bed that where the data came from, here's how to adjust for it.
It's always rotating for us. Never use
I
any
wouldn't
grade
say
six.
that. I wouldn't say it's always rotating for us. There have been times where it hasn't rotated. It's also if it's not square. So even if it's rotating, but if it's square, you use an equivalent diameter.
And then
Because
you plug that diameter into the.
Yep.
Okay. Into the other key.
yes, yeah, I'm sorry. Into into this thing.
Okay. So if it's non-rotating or non-square,
Yep.
do you use this D?
Yep, use it. And this is a little bit of a puzzling discussion right here. I don't know why they're going into this type of detail, but you kind of tell from the pattern of what they use. Like this right there is an agreement with what's in the table and what's in that discussion. And this one is too. But then when you get down to how to use these right here, it's not 100% clear how they want you to approach it. But I did it in an example somewhere.
And those are the little Ds that are plugged into the case of B, or case of B, one of those.
Yeah, case of B, yeah. Into this.
Okay, and is that little D the small diameter or whatever? What is that little D?
That little d is, okay, so if it's rotating, it's the smaller diameter of the thing. Right? Let's say they're having stress concentration or something like that, but it's just the diameter. If it's not rotating, then we want to go to this equation here and take 0.37 times that diameter and then plug it into that kb.
Okay.
Yeah.
So you plug if it's not rotating, you solve for D sub, whatever that is.
DE, yeah.
D sub E and then plug it.
Yeah. And if it's not round, let's say if it's a rectangle, you could get this and then get the E is an equivalent diameter.
And that's for a non-rotating rectangle or any rectangle?
I think it's any any rectangle. Usually the rectangle would be a weird situation for us to be rotating a rectangle.
Mhm.
Not if you're turning down a kitchen table, like on a lathe. That would be normal. That would totally good. But most other times for us, so we're rotating.
For this like essay problem that we just did, if we were to calculate like the number of cycles together, like n,
Did we not finish it? I'm sorry.
I think that might have been, I might,
No, I think I forgot to finish it.
yeah, just a quick question about that.
Okay.
Like n is given as like sigma AR over a to the power of 1 over b for like that stress.
Yep.
Since this is just like a bar without any like grooves or notches or anything, we don't have to consider like notch sensitivity.
No.
It's just
It
purely.
didn't mention anything about it. So
Gotcha.
we're gonna go ahead and pretend like it doesn't have anything.
Okay.
So that, and so like yeah, you're right. We need to go n is equal to our sigma. Oh, and so by the way, we could also, it's totally fine to have this as tau in this case because we adjusted for our endurance strength. Our endurance strength is now a shear endurance strength, even though we didn't put anything in S or anything onto the thing. So we've converted it into a shear endurance strength. So we go tau over A, and then, over the 1 over B. Right? So in that case, for us, it's gonna be 40 KSI over our 221.1, call it, raised to the 1 over negative 0.1993. And we should be so happy as to get 5,300 cycles. And once again, I'm not, so here's 1,000 right here, and here's, so there's 2,000, 3,000, 4,000, actually it's pretty damn close right there, 5,000 cycles to get right there, so. Pretty close.
What is the A and B? Or what are the A and B?
I just think of them as being a curve fit, where this line right here, they have that line, that spot, and this spot, and they found a coefficient and an exponent that would fit to that. All right, so the actual sometimes we'll use S, sometimes use sigma. I don't know. We could just go S is equal to A times N over B. That is just that curve right there. Cool. Another one?
So, sorry, I just lost the train of thought.
I do that all the time.
Yeah, the table that we're talking about just now with the areas of non-rotating geometries, we've never talked about that. We have,
Maybe quickly.
right?
Have there been an example? I thought they were in a problem set. I think it had a little bit. I don't know. I think so.
Wait, sorry, I think I missed why you changed it to tau, or n equals tau over a.
I was just trying to be accurate for the situation, because you'll notice that this was always torsion, right? So we said we had completely reverse torsion. This guy right here, this converts it to, you could even, they don't do it, but you could call this an SES. Sometimes we'll put an S next to something if it's specific to a shear thing. Remembering that 0.59 is for the same exact reason that we would use 0.577 to get like turn the yield strength into the shear yield strength, right? We're using the von Mises, and if you calculate out 1 over the square root of 3, it turns out to be that 0.577 thing, and that's like a conversion factor for shear based on that idea. And so that's for the similar idea, that's what we've done here. So I decided not to call it sigma because we are dealing with the shear and put it in there like that. What would you like to see? Nope.
So the next one also is the and then the reverse is just like
Well, I'll do this one. Is that really
Dr. Zhu,
Yes.
are we gonna have any questions on like design, like reliability, like the graphs of like the bell curve?
No.
Okay.
I thought it was a nice thing to add into the semester, but not something that's like a real high priority.
Thank you.
I would, but I'm not going to. I like to ask an ethics question. So that I could use it on ABET. But I'm not gonna. Maybe on the finals, which you know, right?
Would we be comfortable like doing the Linker, Soderbergh, and modified Goodman lines, like wrapping them by hand?
Yeah, I mean, I was just about to bring up this one right here. It's to do that kind of thing. My biggest priority is Goodman most of the time. Because I think it makes the most amount of sense. It's the most simple. It's the one you see most often, at least I have. And makes the most amount of sense when you keep with the theme of apples to apples. The ultimate strength breaks and falls apart. The endurance strength means that it broke and fell apart. So those are good things to compare when doing the ultimate and mid-range. So this guy right here, they gave us a problem, and I'm not sure if I did write it up. Okay, cool. I didn't give myself enough room right there. Let's do it. All right, so first off, this is back in the day when I think I used to ask a bunch of questions, a step-by-step kind of question things. I don't quite do those as often. The 1020 hot rolled steel has a filleted transition and is subjected to a fluctuating axial load that varies from 5,000 pounds in compression to 20,000 pounds in tension. The fully corrected endurance strength is 19 KSI, yield strength is 30, and the tensile strength is 55. The notch sensitivity is 0.8. And so to draw these lines, and do I have my ruler? I don't have my ruler. Do you have your rulers? I can. I have my. Do I? I have my wire. I lost my ruler. I have my old Yale thing. So I was using this for a long time. Oh, can I borrow your ruler? Thank you so much. So let's see. The Langer line is just going to go from 30 to 30, right? And of course, I think I would. I'm kicking myself. Me in the past. Okay. I was trying to do a better job of keeping my graphs symmetric. This is not symmetric. That's 60 and 35. Okay, and so the Soderbergh goes from endurance strength, which is right about there, to yield. So right about there. So it just disappeared. My line just disappeared. What do you think of that? Oh, look at that. So where's my mouse? Yeah. And let's see, my modified Goodman line. I've got good green. Goodman should be green, right? That just makes sense. Yeah, that goes to 55, so it's right there. So, not doing a great job in that. Calculate the mean alternating stress, taking fatigue stress concentration into account. So what is this? 33.375, 5 inches, and 0.4. So we get ourselves an R over D, 0.4 and 3.375. It's getting tired, you can see 1.1185. And then a big D over D. It's not approximate, it's these. Is 5 over 3.375 with 1.481. So if you, go to the graph with these in it. These would be this guy. And you have tension, so it'd be very similar to this right here. And we have one, so close to 1.5 and close to 0.118, so close to right here. So you're right around is there, and I said that was close to being 2, and that is close to being 2. So KT is approximately 2.0. And now but we know this is going to be fatigue, so we have to use the notch sensitivity. So 1 plus, they gave us that this is 0.8, so you're going to have to look it up. The KT is 2.0 minus 1. So we end up with a fatigue stress concentration of 1.8. And then we also need to use the smaller of these and also the thickness, which should be said somewhere. Oh, we have thickness 3/8 inch thick. So the A to use here is DT, where the D is a width, not a diameter. 3.375 times 0.375 or 1.266 square inches. And they gave us that this was going from negative 5,000 to positive 20,000. So we'll go with FA is equal to F max minus F min over 2. And so that's going to be 20,000 minus 5,000. So we end up with 12,500 pounds. And FM, F max plus F min, but because it's negative, it's going to be less than the other one. Oops. $7,500. So you get your sigma A is going to be the KF times FA over A. So we have 1.8 times 12,500 over 1.266. And that ends up being 17, I'm just going to turn it into KSI, 7.8 KSI. Sigma M, KF, FM over A. Um, 10.67 KSI. So keep going green, they must be ready for Christmas. The Langer is simply going to be the yield strength divided by sigma A plus sigma M. It's really the maximum stress. So we were told this was 30, and then we had the 10.67 and the 17.78. And we get 1.05, and I broke my own rule on this answer here. That's okay. I'm not mad at me. The Soderberg 1 over sigma A over SE plus sigma M over FY. Sigma M 17.78 over 19. $10.67 over 30. And 0.77. So you go die sometime. Good friend, good one. Sigma A over SE plus sigma M. I say that. Let's see. 17.78 over 19 plus 10.67 over 55. That's all over 55. Got a couple of teachers lost a few bits. That's more. And then, in order to find I guess this is asked for the reversible stress. I'm out of room, but I'll read up onto the next, onto the previous favorite here. We want to find where first of all, we want to plot the dot. So our dot should be at 10.67 and at 17.78. So that should be kind of halfway over there. So we should be underneath the liner. So probably right in there. Like we're almost on liner, right? Because our liner is like 1.05. So we're almost on that line. Shouldn't surprise us. For this next part, where we should try to, what we're going to aim for is we're going to go through our dot and get up to right there. So whatever we get right there, that should be our equivalent reverse stress. Or they also, in the 11th edition, they call it sigma subscript AR. That should be equal to sigma A divided by 1 minus sigma M divided by SUT. So that ends up coming out to 17.78 divided by 1 minus 10.67 divided by 55. That's basically 55. And that gets 22.06 KSI, which is pretty close to what we have right there. Graphical movement around things.
Is for the unsignal reverse, that's just we draw a line from is that the ultimate to
through our point, through our load point.
Gotcha.
Which was right there and kind of like somewhere right in there. Got it.
Where did you get those from? Got it.
You know where in the book it walks through at least the sigma A and the sigma M? I've been flipping through, but I'm having trouble with finding.
Oh, no problem. I mean, it was a really good question. feeling comfortable with the book. Unfortunately, a lot of times this is what you're getting tested on. I hate that, but I mean, a certain degree. All right, so yeah, you can do the FA and the FM or the MA and MM all the way through, carry them all the way through, or you can find your sigma A and your sigma M early, and then work with those. You're welcome. Thank you for coming by. All right, let's see if we can find. It's usually in the fluctuating category. So we get done with this,
Yeah.
and there you go, right there. Here's where it begins, right in here. Right. So, like I was saying, you could do this portion of it, or you could just go maximum and minimum, and then find the maximum and minimum stress, and do this same idea to it. So I'm not sure which way the book goes more than one way or another, but this is where it gets introduced, and they start talking about it. So this right here is identical to what was just on the last page. It's just one you could do the maximum and minimum, turn them into the alternating and mid-range forces, or you could do it to the stresses. And I've never really read this section right here. I don't know. I skip over it or anything like that. It's like they do a lot of monkey business with graphs.
But so does the M does the M go on the x-axis? A goes
Yeah. And it's almost I really associate it with this graph right here. Right, that graph right there is sort of like they probably observed this and then were inspired to do all the Soderbergh and the Goodman and the ASME and all those other things because they saw this data collecting in a kind of a way they drew a straight. So this being the straight line is really sort of the Goodman line. And if you read some of the history of it, Goodman kind of came before the rest of them. They all tried to like improve upon what he did. And he survived them all. Yay for Goodman. Hope his family's rich. At least comfortable. I hope they get like more than just, yeah, our great granddad was Goodman. We live in Florida. I'm hoping for my grandkids to leave something, a large guitar collection. I had two friends from Tennessee come over. There's a band, obscure band, playing in Hamden, which I didn't even know that where Hamden was. I got confused with Haddam. There's a lot of the same letters. King's X. Anybody have heard of King's X? Of course you have, because it's a progressive rock band from like the peak in like 1991. But my friends were like big time fans, huge fans. I had to listen to them. They were terrible. But they really enjoyed it. They had to show off all my guitars. And everyone asked, how many guitars have you got? And they got to see that. Because I just kept pulling them out. Oh yeah, I forgot about this one. Oh, I forgot about that. I gotta put them all away, by the way. What do you think they're doing around there?
56,000 monthly listeners.
King's X?
Yeah.
That's not bad. So, or is that bad?
I feel like I was expecting less.
You think less?
If they're terrible.
Well, there's a certain Christian element to them.
Mm-hmm.
So but they're more spiritual, and they're very progressive. Same three people since like 1979. They like each other. They must like each other. They look like me.
No, I said they look pretty chill.
They look pretty chill. They are pretty chill.
Which is not to say you don't look chill.
And then I
Yeah,
no,
but
thank
different
you.
genres.
And but my buddy Daniel had his picture taken with the Doug. Doug plays a 12-string bass, by the way. Very cool instrument. One. You hold 3 strings down at a time. That's a lot of finger pressure. Guy from Cheap Trick plays it. Also, sometimes the guy from Pearl Jam. You hear at the beginning of Jeremy? Boom, 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 boom. You know what I'm talking about? That's good. That's a 12. That's a 12 string. Should play it now. This is what I'm playing. Great song. I mean, it's a dark subject, but it's pretty simple.
Thank you.
More questions? You burned out. You're tired.
Yeah.
You're sick of this. No. Yes. Better. How better spend with your on your own? No. You still you have questions. The guy, the singer lost his voice. Like he's 75 years old. For one, I don't know, age.
Wait, no, no,
The singer from King's X. Oh, was I still talking about Jeremy? So it was such a small part.
Oh, you don't.
I knew.
You're not interested.
But does it really matter because it's gonna be the same circle anyway?
That's not wrong.
Yeah,
But did see people.
I think she knew the more extra deals for business. I'm not
So
sure.
if you go like, King's
So,
X,
no, it's not.
Oh. And they have this in the space bar.
Oh, Space Forward, okay. This was a soccer name. Like, I also said I was gonna be thanks.
Thank you.
Thank you.
Got it.
Yeah, I don't think I have calluses for.
Look how many tuners.
Yeah.
I didn't think it was very good. I was like, oh boy, we were even listening to them on the way down to the custom, back on their studio albums. I was like, this is kind of terrible. But I kept an open mind.
Thank you, Dr. Deal.
Thank you, George.
See you soon. So I think the band Yes is also in Connecticut sometime around now.
Really? Yes?
Yeah.
Yeah, but there's a whole lot of people in Yes that
I
we're
think
not in
they're all
Yes.
suing each other. I know it's Steve Howe, who's the guitarist. For
Yeah.
I really like that guy. I don't know. I might have actually missed it. I don't know when they're playing.
That's the deal.
Yes.
In the future exams, we often move BDR garage hours for exams.
You what?
We move our location for exams. Like whenever people need those rooms in Mason.
Oh, okay.
Like Beth has asked us before, like, can I give an exam in here? Can you guys